Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Coupling of Angular Momenta and Selection Rules from paper Quantum Mechanics. So students, let us see what we are going to learn in this module. In this module, we will get to know the vector addition of the two independent angular momenta. We will learn the rules for the allowed values of the total angular momentum which are obtained by the coupling of two angular momenta. We will learn through a specific example the allowed values of J for the given values of two angular momenta and the corresponding M values. We will study an example of constructing the states for coupling of the uncoupled state using the technique of lowering angular momentum operators. Having introduced the coupled and uncoupled representations and defined the C coefficients in the preceding module, we shall here discuss the selection rules for the non-zero values of C coefficients for J1, J2, M1 and M2. We shall find that for addition of two angular momenta of values J1 and J2, the allowed values of the total angular momenta J run from J is equal to J1 plus J2 to modulus J1 minus J2, where J varies by integer and for each value of J, there are 2J plus 1 values of M. So, M can take up the values going from plus J to minus J and M is equal to M1 plus M2. We begin with the selection rules for allowed values of J and M. In order to find out the allowed values of J for given values of J1 and J2, we proceed as follows. Using the relation operator Jz is equal to operator J1z plus operator J2z and operating on the state ket Jm, we get operator Jz acting on ket Jm is equal to operator J1z plus operator J2z acting on ket Jm, which is simplified to obtain M times H cut into summation over M1 M2 C coefficient which depends on M1 M2 J1 J2 J into ket J1 J2 M1 M2. This is equal to summation over M1 M2 C coefficient which depends on M1 M2 M J1 J2 J into operator J1z plus operator J2z into ket J1 J2 M1 M2, which equals M1 plus M2 into H cut into summation over M1 M2 C coefficient which depends on M1 M2 M J1 J2 J into ket J1 J2 M1 M2, that is summation over M1 M2 M minus M1 minus M2 into C coefficient which depends on M1 M2 M J1 J2 J into ket J1 J2 M1 M2 which equals 0. This equation implies that the C coefficient with the upper indices J1, J2, J and the lower indices M1, M2, M is equal to 0 if M is not equal to M1 plus M2. That is, the C coefficient with upper indices J1, J2, J and lower indices M1, M2, M is not equal to 0 if M is equal to M1 plus M2. Since the maximum allowed values of M1 and M2 are respectively given by J1 and J2, so from the relation M is equal to M1 plus M2, it follows that the maximum possible value of M is J1 plus J2. Now, because M can take only 2J plus 1 values going from minus J2 plus J, it means that the maximum possible value of J is J1 plus J2. For the case J equals J1 plus J2 and M equals J1 plus J2, there will be only one term in the summation on the right of equation 1. That is, corresponding M1 is equal to J1 to M and M2 is equal to J2, we have basis get J1 plus J2 comma J1 plus J2 is equal to C coefficient with upper indices J1, J2, J1 plus J2, lower indices J1, J2, J1 plus J2, get J1, J1, get J2, J2. Using the orthonormality of the states involved, we have the scalar product of states J1 plus J2 comma J1 plus J2 with itself is equal to 1, which equals the square of modulus of C coefficient described by the C coefficient which depends on J1, J2, J1 plus J2. According to this equation, the C coefficient, which is a function of J1, J2, J1 plus J2 is equal to exponential of iota times delta, where delta is real. We choose the phase of the state J1 plus J2 in equation 3 such that delta is 0. Thus, we have the value of C coefficient equals 1. With this choice, we fix the phases of all the C coefficients belonging to J equals J1 plus J2. Let us now consider a state for which J is equal to J1 plus J2 but M is equal to J1 plus J2 minus 1. In this case, we have two possible values for M1 and M2. We can either have M1 equals J1 and M2 equals J2 minus 1, or M1 equals J1 minus 1 and M2 equals J2, or a linear combination of the two linearly independent states, which are the direct product of get J1 J1 with get J2 J2 minus 1 and the direct product of get J1 J1 minus 1 with get J2 J2. Note, there are two such linear combinations. One of them belongs to the set of eigenstates with J equals J1 plus J2, while the other orthogonal combination is a member of a set of eigenstates for which the maximum value of M is J1 plus J2 minus 1. This latter set must be such that J is equal to J1 plus J2 minus 1. Proceeding further in this way to the state J is equal to J1 plus J2 but M equals to J1 plus J2 minus 2. We shall see there exist three linearly independent states corresponding to the values J is equal to J1 plus J2, J1 plus J2 minus 1 and J1 plus J2 minus 2 respectively. Each time M is reduced by unity, by proceeding this way, one of the coupled states which arises belongs to a J value reduced by unity, and in this particular state, M has its maximum value. The lower limit J min is reached when the number of coupled states has matched with all the uncoupled states. We know that summation over J going from J min to J max over the function 2j plus 1 is equal to 2 times J1 plus 1 into 2 times J2 plus 1. We can determine the minimum value of J by noting that J max is equal to J1 plus J2 and the left hand side of equation 5 can be evaluated by using summation going from alpha to J max over J is equal to 1 by 2 into within the brackets J max into J max plus 1 minus alpha into alpha minus 1 bracket close. Using this relation in equation 5, we find that J min square is equal to J1 minus J2 whole square. Since J min is greater than equal to 0 and J min is equal to modulus of J1 minus J2, We thus arrive at an important result that in the addition of two angular momenta, if the eigenvalues of operator J1 square are given by J1 into J1 plus 1, the eigenvalues of operator J2 square are J2 into J2 plus 1, then the eigenvalues of operator J square are given by J into J plus 1, where J is equal to J1 plus J2 minus 1 and so on till modulus of J1 minus J2. The three angular momentum quantum numbers J1, J2 and J satisfy the triangular condition given by J is greater than equal to modulus of J1 minus J2 and less than equal to J1 plus J2. And for each value of J, there are 2J plus 1 values of M given by M is equal to minus J to plus J. These two relations described by equations 9 and 10 serve the basis in the theory of addition of two angular momenta. Now, let us consider an example to illustrate the allowed values of J and M for the case J1 equals 3 by 2 and J2 equals 2. Now, coupling of J1 equals 3 by 2 and J2 equals 2 results in the values of J being less than equal to 7 by 2 and greater than equal to 1 by 2. So, if J takes the value 7 by 2 and 5 by 2, then M will be equal to 5 by 2, resulting in M1 being equal to 3 by 2 and 1 by 2 and M2 being equal to 2, 1, 2. For J equal to 7 by 2, 5 by 2 and 3 by 2, M can take the value 3 by 2 and correspondingly the values of M1 are given by 3 by 2, 1 by 2, minus 1 by 2 and M2 are given by 0, 1, 2. For values of J being 7 by 2, 5 by 2, 3 by 2, 1 by 2, M can take the value 1 by 2 and M1 will take the values ranging from plus 3 by 2 to minus 3 by 2 and M2 taking the values minus 1, 0, 1 and 2. Similarly, the values of M, M1 and M2 can be described for the states given by J equals 7 by 2, 5 by 2, 3 by 2 and J equals 7 by 2, 5 by 2 and J equals 7 by 2. Next we discuss the example of the addition of angular momenta. Note that for given J1 is equal to 3 by 2, M1 can take the values minus 3 by 2, minus 1 by 2, 1 by 2 and 3 by 2. And for J2 is equal to 2, M2 can have the values minus 2, minus 1, 0, 1 and 2. It should be checked from the above table that in the uncoupled representation, total number of states will be 2J1 plus 1 into 2J2 plus 1. That is 4 into 5 equals 20, which matches with the number of states in the coupled representation, with J1 plus J2 is equal to 7 by 2. So summation over 2J plus 1 will give 20 and also the modulus of J1 minus J2 is equal to 1 by 2. Next, the next example of the addition of angular momenta is taking the value of J1 equals 1 and J2 equals 1. Next, we consider a specific example of coupling of angular momenta. We will consider the case in which J1 is equal to J2 is equal to 1. Physically, we have here a two-particle system in which the angular momenta of the two particles are equal to 1. Let us assume that the base is composed of common eigenstates of operator J1 square, operator J2 square, operator J1z and operator J2z are known. So, bases get 1, 1, M1, M2, where M1 is equal to M2 is equal to 1, 0, minus 1, 1, 0 and minus 1. Clearly, The total number of states in the uncoupled representation are 3 cross 3, which is equal to 9. Now we want to determine the basis ket j comma m for common eigenvectors of operator j square, operator jz, operator j1 square and operator j2 square, where j is the total angular momentum. As discussed above, the possible values of the angular momentum are j is equal to 2, 1 and 0. Corresponding to the value j is equal to 2, we have the projections m equals 2, 1, 0, minus 1 and minus 2. Now we discuss the subspace of j is equal to 2. The ket for j equal to 2 and m equal to 2 can be written simply as ket 2 comma 2, which is equal to ket j1 is equal to 1, j2 is equal to 1, m1 is equal to 1 and m2 is equal to 1, which equals ket 1 comma 1 comma 1 comma 1. To get the vector j equals to 2 and m is equal to 1, we apply the operator j minus on the left hand side of equation 11 and we get operator j minus operating on ket 2 comma 2 is equal to h cut into square root of within the brackets j plus m into j minus m plus 1 brackets close ket 2 comma 1, which equals 2 times h cut ket 2 comma 1. Therefore, ket 2 comma 1 is equal to 1 by 2 h cut into operator j minus acting on ket 2 comma 2, which equals 1 by 2 times h cut within the brackets operator j1 minus plus operator j2 minus brackets close acting on ket 1 comma 1 comma 1 comma 1. Now operator j1 minus will operate on particle 1 and operator j2 minus will operate on particle 2 and we shall get operator j1 minus acting on ket 1 comma 1 comma 1 is equal to h cut times square root of within the brackets j1 plus m1 into j1 minus m1 plus 1 bracket close acting on ket 1 comma 1 comma 0 comma 1, which equals square root of 2 times h cut ket 1 comma 1 comma 0 comma 1. Similarly, we get the operator j2 minus acting on ket 1 comma 1 comma 1 comma 1 is equal to square root of 2 times h cut acting on ket 1 comma 1 comma 1 comma 0. The net result is ket 2 comma 1 is equal to 1 by 2 times h cut into the ladder operator j minus acting on ket 2 comma 2, which equals 1 by 2 times h cut into within the brackets operator j1 minus plus operator j2 minus bracket close acting on ket 1 comma 1 comma 1 comma 1, which equals 1 by square root of 2 into within the brackets ket 1 comma 1 comma 0 comma 1 plus another ket 1 comma 1 comma 1 comma 0 brackets close. We use the ladder operator j minus again on the state described by the ket j is equal to 2 and m is equal to 1 to get the ket j is equal to 2, m is equal to 0, and we get ket 2 comma 0 is equal to 1 by square root of 6 into with the brackets ket 1 comma 1 comma 1 comma minus 1 plus 2 times ket 1 comma 1 comma 0 comma 0 plus ket 1 comma 1 comma minus 1 comma 1. In this way, the states 2 comma minus 1 and ket 2 comma minus 2 are obtained by operating the ladder operator j minus on the preceding kets. We thus get ket2 comma minus 1 is equal to 1 by square root of 2 into within the brackets ket1 comma 1 comma 0 comma minus 1 plus ket1 comma 1 comma minus 1 comma 0 and ket2 comma minus 2 equals ket1 comma 1 comma minus 1 comma minus 1. Next we discuss for subspace j equals 1. Let us now proceed to calculate the vector described by ket j is equal to 1 and m is equal to 1. Note that this vector must be a linear combination of the two basis kets, that is ket1 comma 1 comma 1 comma 0 and ket1 comma 1 comma 0 comma 1, the only ones for which m is equal to 1. Let us set ket1 comma 1 equals alpha times ket1 comma 1 comma 1 comma 0 plus beta times ket1 comma 1 comma 0 comma 1 with modulus alpha square plus modulus beta square equals 1. This must be orthogonal to the state described by ket2 comma 1. For this, it is necessary that alpha plus beta must equal 0. Now choosing alpha and beta to be real and by convention alpha to be positive, we write ket1 comma 1 is equal to 1 by square root of 2 into within the brackets ket1 comma 1 comma 1 comma 0 minus ket1 comma 1 comma 0 comma 1. We now apply the operator j minus on this state to get ket1 comma 0, on which by applying operator j minus we get the ket1 comma minus 1. Thus, by using the same technique as used above, we have ket1 comma 0 equals 1 by square root of 2 into within the brackets ket1 comma 1 comma 1 comma minus 1 minus ket1 comma 1 comma minus 1 comma 1. Next we discuss the measurement of Bragg angles theta and interplanar spacing t. Now the basis ket1 comma minus 1 is equal to 1 by square root of 2 into within the brackets the basis ket1 comma 1 comma 0 comma minus 1 minus basis ket1 comma 1 comma minus 1 comma 0 brackets close. It is interesting to note that the expression described in equation 20 does not have the vector defined by basis ket1 comma 1 comma 0 comma 0, although it just corresponds to m is equal to 0. We shall see in the next module that the C coefficient corresponding to this is 0. That is, the scalar product of 1 comma 1 comma 0 comma 0 with ket1 comma 0 is equal to 0. The state next we discuss the state defined by the ket j is equal to 0 and m is equal to 0. To calculate the last vector, we note that this is a linear combination of the three basis ket for which m is equal to 0. We write the basis ket 0 comma 0 is equal to alpha times the ket 1 comma 1 comma minus 1 1 comma 1 comma 1 comma minus 1 plus beta times the basis ket 1 comma 1 comma 0 comma 0 plus gamma times the ket 1 comma 1 comma minus 1 comma 1 with the modulus of alpha square plus modulus of beta square plus modulus of gamma square equals 1. The ket described by equation 23 must be orthogonal to the ket 2 comma 0 and ket 1 comma 0. Imposing these conditions, we get the two conditions alpha plus 2 beta plus gamma equals 0 and alpha minus gamma equals 0. These relations give alpha equals minus beta equals gamma. Choosing these to be real and taking alpha to be positive, we get ket 0, 0 equals 1 by square root of 3 into within the brackets ket 1, 1, 1, minus 1 minus ket 1, 1, 0, 0 plus ket 1, 1, minus 1, 1. With this, we complete the construction of ket Jm basis for the case J1 is equal to J2 is equal to 1. So students, let us now summarize what we have learned in this module. In this module, we have learned the vector addition of the two independent angular momenta. We have learned the rules for the allowed values J of the total angular momenta obtained by coupling of two angular momenta. We have learned through a specific example the allowed values of J for the given values of the two angular momenta and the corresponding values. We have studied an example of constructing the states for the coupling of the uncoupled states using the technique of lowering angular momentum operator.